All right. So now that we're recording,
Yeah, we will be working on a couple of.
yes, today in the guided practice, part of that will be R code, but not like in our help session where that's our explicit focus. This is on test prep. Okay. All right. So first off, most of you have taken 309. If not, you've taken some other stats course previously. For most of you, I'm guessing the whole process of a decision tree is new, right? The rest of the course we've talked about regression and probability rules. This is original material as far as I've observed. So we'll start from there, if that's all right. So a few notes I wanted to mention. First, when you're building a tree, it moves chronologically. Whatever decision you make first happens at the left side of the tree, and you progress as events unfold in time. Because they progress in that dimension, anything on the right side of the tree is conditional upon the previous branches. So if you're making multiple decisions, then the probabilities of events that happen later are all conditioned upon what's already happened. And lastly, perfect information, which many of you had questions about recently, means you have ones and zeros at some point in your probabilities. So on your homework last week, and maybe it's this week, you have the opportunity to ask basically a consultant, and they can help give you better probabilities of what's going to happen. If that consultant has perfect information, then the probability the consultant is right is 1 and 0. Because they know what they're talking about. So without further ado, here's your problem. Congratulations, you are the founder of a hot tech startup. You have all of the stock. But you're ready to sell. You have a private equity firm that wants to just buy the company from you outright for $2 million. Or you can IPO. You figure that you have a 10% chance of winning, so to speak, beating the IPO lottery and getting $5 million out of it, but a 90% chance of just $1 million. However, you have a friend from McCombs who specializes as an IPO consultant. She guesses 75% of successes correctly and 85% of failures correctly. In this case, interpret a success as winning $5 million and a failure as yielding only $1 million. All right, for those of you just walking in, we're doing guided practice today for the review. So go ahead and try on this question. So, based off the consultant's advice, what should you do? Hint, at this point, build a decision tree. Try to calculate the appropriate values. Okay, good. That's good. I was hoping it wasn't too slow. All of these problems you have with business decision, whenever I get higher, something to help, like homework. I was like, oh, I guess I'll just stick with that. Should we give it 5 minutes? A little less than that because the tips on this page. I'll go ahead and give you the hint here. let's go ahead and take the first step together. What is the first node in your tree? The square, right. What are you doing in the square? Square is the decision, so it's what? Yep. This is to hire a consultant. This is not. Okay? So let's start from the bottom. If you don't hire, what happens next? Raise your hand. Yes. Not going to hear you at the door. Yeah, now we need to choose what you want to do. Do you want to risk the IPO? Or do you want to just sell? All right. What happens if we just sell? Is there anything else that happens? No, you just get the money. How much? Can you all see the board? Good enough? All right. What happens if we choose to IPO? What's our next? What goes on the end of the IPO branch there? Say it again? Probability node, yep. What are the probabilities that are coming off of this thing? Yep, say it again.
0.1 of success, 0.9 of failure.
Alright, so we have a 0.1 chance of success, 0.9 chance of failure. Success comes out to the tune of $5 million. And failure comes out to the tune of $1 million. I don't know about you, but that's a pretty good failure. Of course, I guess it's how many years and sweat equity you put into the company. Alright, is there anything else that happens if you don't hire the consultant? No. Right? Because chronologically, you need to choose what advice and input you're gonna have, and then you make the choice about what you're going to do. So if you hire the consultant, what happens next? Are you gonna make a decision, or do you? But you first wait to see what the consultant says, right? That is not your choice, so it's a probability node. There's a probability that the consultant says you got a good chance for success, and a good probability that you have a better, worse chance at failing. So this is going to be her forecast of failure. This is forecast of success. Is this moderately legible for those of you in the back? Hopefully I'm talking through it loud enough you can pick up what's going on. Alright, once you've seen the information from the consultant, everything else proceeds with the same shape at least, as if you hadn't asked the consultant at all, right? You've received all the input from the consultant, now you need to choose what you're going to do. You can choose to IPO, or you can choose to just sell, or you can IPO. Yeah, there you go. All right. What are the financial values for each of these stems?
This one would be sell.
IPO.
IPO, sorry.
No, that you're correct. Sales on the bottom.
Okay.
IPO on the top. All right. If we were to have the consultant forecast success for us, and then we proceed to IPO, how much do we make it successful? 4.9 million. Why 4.9? And to pay the consultant. That very top branch, 4.9. Similarly, if our IPO fails, come out with 0.9 million. That's the next one down. 0.9. All right, what if we choose to sell to the private equity company at this point? $2 million, right? 1.9. We've already hired the consultant. Even if we choose not to use the advice, we still had to pay her. 1.9 million. If the consultant forecasts a failure, have our monetary values for monetary results change? No, just the probabilities, right? So same monetary values. As the top, right? 4.9, 0.9, and 1.9. All right, we know our end results, and we know we'd rather choose the maximum possible result over the minimum over anything else. So what we need now, we've written the values we need to calculate the probabilities through. Right? Certain points at which all these probability nodes, we need to know what's going on. All right, so what probabilities do we have to begin with? Just for reference sake, let's call forecasting a success F. S actually succeeding. Okay? What are we given in the prompt? Probability of success is 10%, 0.1. Then we have the advice. Then we have the advice of the consultant. Right? Advice from this consultant is conditioned upon what she's guessing correctly. So she guesses 75% of successes correctly. So that is given that the IPO will be a success. What's the probability she forecasts it as such? So just like Sai has right there. That's 75%. All right, that's pretty standard for these problems. And then I threw in a, I don't know if I would call it tricky, but a little slightly different way of phrasing it. What does it mean if she forecasts 85% of failures correctly? What probability is that describing? Say it again one more time. This probability of not forecasting is not successful, given that it is not successful. That's F bar given S bar in probability notation. Right? Because if she's going to guess 85% of failures correctly, it means you're only looking at the failures, so hence given failure, what's the probability she predicts it correctly. So what's the probability of forecasting failure given it will fail? That's 0.85%. All right. Can we plug any of those into our tree immediately? Right. Toddler chop here. So forecasting failure.
Can we plug in?
We have that. Note that this is P of F bar. We don't have that yet. This is P of F bar, this is P of F. Right? How about here? 1.1, we already have this. Good job, guys. 0.1 is P of S. And this makes it P of S bar. Try that again. Okay, so we have currently conditions. Our conditional probabilities are based off of success or not. The tree, you forecast first, and then you see success or not. So what we need probability of success, given she's forecasting success, and its inverse, which is just adding a bar there, as well as the probability of success, given that she forecasts failure. We need to reverse the condition, right? We have F given S. We need S given F. What tool do we have for reversing conditions? Bayes' rule. Okay, do we have all those parts? If you're not familiar with Bayes' rule, it will be displayed very large on the screen in just a moment. Short answer, yes. We have F given S, the probability of S, the probability of not F given S, or excuse me, yeah, not F given S, the probability of not S. Save us time, that's equal to 0.35. Right, so that very top node is 0.35, which means the bottom part is 0.65. We do the same thing for the next branch down, which has a success. So the probability of success given she predicted failure is 0.031. Which means failure is then 0.969. So if she's predicting you're going to fail, it looks like you'll fail pretty epically. Okay, we filled out the probabilities. Right? All except for P of F and P of F bar. Note that P of F is what you found here. Yes?
How do you get 0.031 for the IPO?
So you use Bayes' rule for this one. P of S given F bar is P of F bar given S times P of S, the whole by. Oh, so that's basically 1 minus P of F bar by S bar.
Right? Because anytime you're given a probability, you know what its inverse is. Right? So F bar, the inverse would be P of F given S bar. Good question. All right?
Any questions? Sorry? The denominator?
That says patience. Says P of F given S times P of S, so your numerator, same thing, plus P of F given S bar times P of S bar. Okay? I call that the expanded Bayes rule, because the simpler version is
Just
the
P of
denominator
F.
is just P of F. What you need on this problem here is equal to 0.21, and P of F bar is 0.79. Yeah, it's a lot for one blackboard. This will be posted online digitally if you have questions. This also looks a lot like the one on your practice test, as well as the homework you've done. All right, so to conclude, we now need to find our values so that we can make this initial decision, right? And the intermediate decision. So we roll back the values. Start at the top. How do we get the expected value of our first random node? That's circle. an expected value with two possibilities, you multiply the probabilities times their values and add them together. So 0.35 times 0.49 plus 0.64 times 0.9, that circle is 2.32. 2.32. Okay? Oh, so your random node at the top there, the very, very top corner, splits between being a success and not a success given you forecast it as a success. So you multiply the probability 0.35 times the value 4.9 plus 0.65 times the value from failure 0.9. Yeah, that's the node. That's the node value. All right, the next node down is a decision node. What are you going to decide? You have an expected value of IPO at $2.3 million and the known value for selling at $1.9 million. So you choose the maximum, 2.3 million.
So
Yeah. So the value of this node is right 2.3 in the middle of the node 2. Which one? This square. No, the top one. Just so they can see the value. All right, and we do the same thing for each of the other circle nodes. Right, meaning expected value. You have two possible outcomes and probabilities between the two. So to multiply 3% times 4.9 million times 97% times 0.9 million, you get 1.03. Then if you choose between 1.03 and 1.9, clearly you choose 1.9. Now we have an expected value of, if forecast is success, we have an expected value of 2.32. We have an expected value of 1.9 if she forecasts us being a failure. Multiply each value by its probability, and then add those together. You should get 1.99. Do the same thing in the bottom. That random node has a 1.4. We have to choose between 1.4 and 2. We choose 2. So what do? You hire the consultant? No. You just go ahead and sell it off to private equity. Finish the back part of that tree fairly quickly, but the principles were the same throughout. On a circle node, you need to have a value and probability for each split, for each branch, twig. You gotta stick with the tree metaphor. Multiply the probabilities by the value and add them together. Then as you work your way back in the tree, you decide on the maximum for each square node. Yes? So P of F is the denominator from base rule. Good question. And 1 minus that P of not F. Okay?
75% is P of F given S.
The percent of successes she predicts to be successes. Forecast, that's where the F comes from. Yes? Come again? Oh, I would pick 2. Oh, here? This is a random node. So I multiply my 2.3 times its probability of 0.21 and add that to 1.9 times its probability of 0.79. Because I don't get to choose how she predicts. Okay? If we have time, the last question of the day will also be a decision tree. All right. Happy to answer any other questions on decision trees. Feel free to raise your hand during the rest of the hour, 2 hours. So, first part of this course, what you first got to talk about was probabilities. Here you have a two-way table. And you know that IBM stock, let's take a simple situation. IBM stock can grow by $1 or fall by $1. Those are the only two possibilities. Whereas General Motors stock can do the same, rise or fall by $1. That's the two-way table. Now the question is, what are the marginal probabilities of X? What are the marginal probabilities of Y? And you hear B and C here. What's the probability that the stock price of IBM goes up by 1? And if you know that GM stock is going to fall today, you have insider information, what is the probability that the stock price of IBM goes up by 1, given that information? This one should be a little more straightforward than decision tree. So go ahead and give you 5 minutes to try your best. I'll take over on this question.
I'll go to decision first.
Excellent.
If you have questions, feel free to ask.
There's a hint on the next page if you want.
Mhm.
It shows them what margins are.
Just give them a minute.
Oh yeah, absolutely. It's literally on stage. Right there.
Right. That's a hint. Recall that two-way tables contain joint probabilities. The sums of the rows and the sums of the columns are the marginal probabilities. Also know the definition of conditional probability. P of A given B is P of A intersection B by P of B. So what do you guys know about marginal probability? Anyone? Okay, so marginal probability, if I'm given two variables, right? Here I have variables x and y. And both x and y have two states to them, +1 and -1. So the marginal probability of x would imply that I'm not accounting for y, but for x alone. So marginal probability of x would imply probability of x being 1 and probability of x being -1. Similarly, marginal probability of y would be probability of y being 1 and probability of y being -1. So from here, I think you can say the probability of x being -1 would be nothing but the addition of these two values, right? So the probability of x being -1 would be 0.25 plus 0.15, which would be 0.4. And the probability of x being 1 is 0.6. So these two constitute the marginal probabilities of x. Yeah, okay. Oh, okay. So the marginal probabilities of x would be 0.4 and 0.6, and the marginal probabilities of y would be 0.3 and 0.7. Oh.
You see how these two tables connect? They're different, slightly different shapes, but what we have is 4 different joint probabilities. This one's different because it's describing because it's GM going up and down by 1, and IBM going up and down. Otherwise, these are the same two tables, but this one shows you the margins.
So the question B is, what is the probability that the stock price of IBM goes up by $1? If you notice carefully, this is basically rewording part A. It's just asking for the stock price of IBM being $1, which is the probability of X being 1, going up by $1 rather. So that's the probability of X being 1. So it could be worded in a different way as shown in B. And yeah, that's going to be 0.6. And the third question, if you know that GM stock price will fall today, what is the probability that the stock price of IBM goes up by $1? As you would have guessed by now, that's a conditional probability that given y equals -1, what is the probability of x being 1? And referring to the conditional probability formula that was posted over here. Sorry about that. Okay, yeah, right there. Referring to this one, you know that the values inside each one of your boxes in your truth table are probabilities of intersections. And you have to use this formula over here to calculate the condition probability. So in my case, the probability of x being 1, given the probability of y, given that y equals -1, would be nothing but this 0.05 from this table over here divided by this probability of GM being -1. Any questions? Yeah.
So if you're a visual person, note that here you know you're looking for a conditional probability conditioned on GM dropping $1. Well, so take your GM dropping $1. All you care about is this column. You know that GM is going to drop $1. So this is the only column you're concerned about. And you find that IBM is 0.05 over 0.3. Right? You need to adjust because this is only adding up to 0.3. You divide by that. In a world where GM is dropping $1, IBM gets 0.05 of the 0.3 available probabilities. 0.05 divided by 0.3.
Any questions?
Questions?
Right. Okay.
Confusions? Okay.
Okay. We'll move to the next question. Are changes in IBM stock price independent of changes in GM stock price?
I wish I had a presentation now because then you can see the next page. Probably does. Yeah, go ahead. By the way, I'll go.
Second part of the question, what is the probability that either stock price increases? All right, so for the first part, let's stay here for a second. So you've thought about A for a little bit. Let's talk about B. What's the probability that either stock price increases? In other words, IBM goes up $1 or GM goes up $1. Okay? So recall that if A and B are independent, then the probability of A and B occurring is equal to the probability of A times the probability of B. Or in other words, the joint is a product of the marginals. Okay? P of A is the marginal probability of A. P of B is the marginal probability of B. Also, if you're looking for either A or B, that's simply equal to all of the cells of your two-way table that qualify for that condition. So we're looking for either of them going up. So you add here and here and here because these are all ones. Right? Here's where y goes up, here's where x goes up. So you can add those together. The formula you discussed in class looks a little more like this, which is also correct. So again, the two questions are A and B independent? And what's the probability of either stock going up? All right, who wants to take a stab at A? Are A and B independent? Or is IBM stock independent of GM stock? No, why not? Good. So the probability of them both going up, so probability of A and B, is not equal to the probability of A times the probability of B, which is 0.42. Right on. They cannot be independent. Right? Because if they're independent, they have to satisfy the condition that the joint is the probability of the marginals, or is the product of the marginals. Equal to the product of the marginals. Yeah. Same thing. Okay, independent. One of the implications of being independent is that the joint is a product of the marginals. Okay? Remember, you do get to bring in one sheet of notes to the exam. Just putting that out there. Oh. Yeah.
Yeah.
It'll be posted on.
It'll be posted on.
All right, what's the probability that either stock has a price increase? Well, like I mentioned, you can just add those three cells together. 0.05 plus 0.55 plus 1.5. Right, this gives us the probability that at least one of them increases in price. Alternatively, and what sometimes is easier to use because you have those pieces, is to add 0.6 and 0.7 and then subtract the intersection of 0.55. I think you had a homework problem on this recently. Right, because you're adding 0.6 to 0.7, you've double counted this cell. So you need to subtract one of those out, which is what you're doing right there. Any questions on the general additive rule of probability? Whose name you don't have to know. Okay. I get a lot of questions in office hours about each problems where what application of a rule can give you the answer. First and foremost, I'd like to note that basically everything you can build with knowing what joint and marginal probabilities are and the definition of conditional probability. Right? So to review, marginal is just the probability of an event. The joint is the probability that two events happen at the same time. Happen simultaneously. In this case, A happening and B not happening. The conditional probability, so if A is going to happen, or we know A happens, or it happens just now, the probability that B does not happen is equal to the joint divided by the marginal. Sometimes it's hard to remember which marginals to divide by. You're dividing by the one that's on the bottom, so to speak, of the bar. Don't worry about it. It's pretty door. Alright, probability of A and not B, probability of not B, given A and the probability of A. That's simply taking this and multiplying both sides by the probability of A. And you can get the joint by multiplying the conditional and the marginal. Why might that be important? Or where do we often see multiplication of conditionals and marginals? This right here. The numerator of Bayes' rule. Not only that, it shows up twice in the denominator of Bayes' rule. Okay? Here's the two rules we just discussed. Here's the question we had earlier on how do you get P of F? Right? We wanted to get the probability of being forecast as a success in the decision tree problem. This has no other variable attached, so it's a marginal probability, just one event you're looking at. And to find that, we need the joint of A were taking your exam, I would have, unless you were very comfortable with these rules, I'd have different pieces written down because problems like the ones we've just gone over are solved simply by plugging in the right pieces into the right rule. Okay, any questions? All right, we'll proceed.
All right, we'll look at a problem for the application of Bayes' rule, right? So there's a cancer screening test that detects cancer in 95% of cancer patients, but it also detects cancer in 10% of cancer-free patients. It's estimated that 0.5% of the population suffer from cancer. Suppose a random individual is screened. You don't know if this person has cancer or not. Calculate the following probabilities. First, that the test result would be positive. Second question being that given a positive result, a person is covered. The third being that given a negative result, the person is a non-sufferer. And the fourth being that the person will be misclassified. We'll give you 5 minutes time and we'll be taking questions. right? I think we'll go to the solution now. Or do you guys need a little more time? Can we go to the solution? All right. So the first part of the question is to calculate the probability that the test result will be positive, right? So this, if you recall, is basically the denominator of the base formula. So I'm going to be defining something. T is testing positive, S being that you suffer from cancer, and M being that you're misclassified. So in your question, you're given probability of T given S. That is, if you're a sufferer, the probability that you test positive is 0.95. If you're not a sufferer, the probability of testing positive is 0.1. The probability of you actually having cancer is 0.005. And yeah, so these are what you can infer from the questions. So the first question would be the probability that you test positive, which is P of T. That can be found out by multiplying the conditional probability with your P of T. So there's that. That gives you a value of 0.10425. Okay, so the second question is that given a positive result, the person is a sufferer. So we use Bayes' rule here. So you want to find the probability of S given T. We use the Bayes' rule. Probability of T given S times the probability of S. The whole thing divided by the probability of T that you got from the part A. So that actually gives me quite a low value, which means that even though you test positive, there's a high percent chance that you don't have cancer. So, yay. Okay, the next part of the question is that given a negative result, the person is a non-sufferer. I think this one is more important for the test. And as you can see from here, probability of S bar, or that notation is allowed as well. This would be calculated by Bayes' rule again, and that gives me a value of 0.997, which means that if I test negative, then the probability that I don't have cancer is quite high, which is good for the test. And the fourth question is, what is the probability that the person will be misclassified? What do you mean by misclassified? Yeah. So you don't suffer and you test positive, or you suffer and you test negative, right? So that would be the probability of misclassified. That would be the probability that you test positive when you don't suffer from cancer, and the probability that you test negative when you actually suffer from cancer. And that would be 0.09975. Any questions? Yes?
So I just created a tree diagram. Do y'all not suggest doing that?
If there's a reason that there should be sequential, then yes.
Okay.
In this
I
case,
just found that way easier than like trying to plug all the right numbers into
did you get the right solutions?
Yeah, I got all the right solutions.
Okay. The trick is when you're to do that, you have to start thinking in terms of conditional probabilities, and if you do that, that's fine. Sorry, I shook my head gently because what I was actually going to show everyone on the next slide was if you're like me,
Yeah, that also.
and you, so these are correct statements. These formulas are good. If you want to use Bayes' rule, have at it. For me, Jared Fisher, personally, I'd rather do a few small steps as opposed to one big step. So my technique, and maybe this helps you, is to first just get your two-way table together. Right? So you're given probability that you suffer from cancer, 0.005. You put that in your margin. And you have two conditional probabilities. Well, you multiply those conditionals times the P of S, and you get the joint between T and S to put there. And you do the same thing for T and not S. And you get a 0.0995 there. From here, you've got three numbers, and you can simply add and subtract from 1 to get the rest of them. Yes? Okay. So notice that he's doing, or the formula here is doing t given s bar times p of s bar. That is a joint.
I think what she's trying to ask is why isn't the addition of probability of t given s bar and the probability of t bar given s instead of joint? That's what you're asking, right?
So what you need in this question is to add the two joints together. However you get those joints is fine. So you can get those by multiplying t given s times s, t given s naught times s naught's probability, or you can mix and match, or you could also use p of s naught given t naught times p of t naught. Does that help your question? Like it is right here?
Yeah, I think she's trying to ask why isn't it just p of t given s bar plus probability of t bar given
Okay.
s instead of
That, yeah, we'll describe it more to you.
yeah,
The idea is
probably get back to you on
this is what you want, because you need the total percentage of people who would be misclassified positive and misclassified negative, and you'll want to add those together. The conditional doesn't give you that. So I think it's, this, especially part D here, is kind of easier to see if you fill out your two-way table, right? Because in this two-way table, we see that 89% of the people who don't have cancer also don't get classified on the test. Or 89% of people both do not get classified having cancer, and they don't have cancer. So that's good. Little under 0.5% of people have cancer and get tested for it, and get classified as having cancer, which means that this group and this group are misclassified. So simply add those together to get your result. Oh. Okay? It's math. All roads lead to Rome. If you like doing this way or with Bayes' rule, have at it. Any questions? All right. Let's play a game. You get to flip 2 coins. If they're both heads, you get $2. If they're both tails, you lose $5. If it's either mixed heads and tails, you get $1. Do you want to play this game? Or in other words, what do you expect to win by playing it once? Also, what's the standard deviation of winning? Or of the winnings, excuse me. How much do you expect your expectation to be? Okay.
Yeah, I think that's better. I think you should skip the next example. One should be good.
Maybe just talk through it in like 90 seconds.
Yeah.
For time's sake, I'm going to go ahead and give you your hint. Please recall that for discrete random variables, for continuous random variables, you have the same equation, but the integrate is the sum. But here we're just going to sum over the value times the probability. And for variance, you multiply the squared deviation times the value, times the probability, and sum those up. Okay? Should be the same equations you've seen in class. If you have your computer open, R does it pretty fast too. Okay. So, with the expected value, multiply your probabilities times your winning values. So 2, -5, and 1. Multiply those times the probabilities and add it together. You get -25 cents. Sorry, there's a double negative sign there. That's not supposed to be. Try that again. Variance, you do similarly. Subtract your expected value from each of your possible values, square those, and multiply it by the probabilities. Finally, add them all together. Taking the square root of variance gives you your standard deviation. You can certainly do this by hand. There's only 3 or 4 possibilities depending on how you draw it up if you combine heads, tails with tails, head. But this is, after all, a class that uses R. Let me show you how to do that real quick. Okay, I'm going to make a vector of my probabilities and a vector of my values. I can gain $2, lose $5, or gain $1, right? Easy enough. Let me get my expected value of x. Maybe I'll just call it expected value. It's going to be the sum of the product of the probabilities and the values. Right? Isn't this exactly what the algebra said a second ago? Where'd the slides go? Yay for Max. Right? We're going to sum over values times probabilities. And variance, we're going to sum over probabilities times squared errors. So sum over probabilities times values, which means for the variance, we're going to sum over probabilities times values minus expected value squared. I am simply programming the algebra equation into R. And it does that for the whole vector, and then when you tell it to sum, it takes all those pieces and compresses it to 1. Let me show you. Here's my probabilities. Oh. There's my probabilities. There's my values. I can multiply them together and then sum them up. And the variance does the same thing. My variance is 7.68, which means my standard deviation is 2.77. Do you want to play this game? Yeah, the correct answer should be no. You should be paid to play this game because on average you will lose money. All right, any questions? Just applying the definition of expected value and variance. Yes, here and then in the back. Because you can flip tails and heads or heads and tails. Because you have 2 coins, right? So you have 4 possibilities. In the back? Yep. Sure. And there's our code to be posted online as well. Okay. For the sake of time, I'm going to run through this problem quickly. So let's say annual car sales at a local dealership follow a normal distribution. They average 500 sales per year. And most years they sell between 400 and 600. I changed that. Thousands of dollars. Oh well. Okay. I changed this to be money for the cars. I guess it didn't say that. About 400 to 600 cars. So first off, what's the standard deviation of their annual sales? And then what's the probability of selling between 456 and So the first one, recall the 68, 95, 99.7 rule, which is all the details right there in the name. Because in a normal distribution, one standard deviation out, and the mean has 68% of the possibilities. Two standard deviations has about 95%, and three standard deviations has about 99.7%. Approximately, right? That's the rule. To get the probability between 2 points, we use p-norm. Oh, that's where I messed it up. All right, I'll fix these slides before you see them again. The answer's still the same. Right? If you want the probability between 2 points, p-norm only gives you the probability to the left of in the distribution, correct? Right? So if I took the p-norm of 0, I would get 0.5 because it gives me the area to the left of 0. And if I want the probability between these 2 points, I take the p-norm of each point and subtract the smaller one, thus getting the area under the curve between those two values. Right, if you have questions on this, we'll be happy to take them after. Because I really want to get to this. This is the other big part of it. You notice the class kind of covered probability, decision trees, and now regression. Hopefully you've all had regression before this course. But for review, those of you who have laptops and want to follow along, you can read in the CSV file for the Holmes data set. Yes, that looks like a very long address to get your CSV from. However, that's the same as the other data you've loaded for your homework. And except instead of, I don't know, stockprices.csv or whatever the last one's called, this is houses.csv. Go ahead and take a moment to get that loaded. Once you get it loaded, proceed to create a model of sales price forecasted by the living area of a home. In other words, use square footage to predict sale prices in the home. These questions are very similar to what you could be asked on the exam and practice exam. Let's practice it.
My mouth's going dry. Computer's locked. Yeah, it's locked. I'll unlock that real quick. Take a sneak peek at what I wrote. I left them very easily empty.
This data set it had multiple columns, right?
Yes.
You did leave out all the other columns.
In the progression. I texted the professor. She made back to me and said, no, we've only covered single X.
Right.
Starting with that URL, it's the same as on the homework. All right, if you've had a few moments now to get your code up and working, you should have something that looks like this. Sorry. All right, has everyone been able to get at least to the linear model summary? Okay. So you're asked, is living area a significant predictor of sale price? How can you tell that from the linear model summary? Which one? Which one? The very bottom right one? Or the bottom one on the top top right? I guess I should have maybe defined different colors.
Well, the bottom one on the top right and the very bottom one should be the same.
Correct. Why is that?
I never looked.
Okay, no, that's the extra trick question. No, they're the same because you only have one predictor. So your test on the whole model is equivalent to being a test on that one predictor. So yeah, the p-value on your predictor living area is smaller than the computer can count. So definitely below 0.05. How much of the variation in sale price is predicted by living area? Yes, it's R squared. In this case, R squared is 50.75%. Anytime you see on a test or in a newspaper or something, if they're asking about you the variation predicted by X or the percent of variation explained by X, that's an R squared. Okay?
All right. How much do you expect the sales price to increase for 100 extra square feet of living area? For that, I need to look at the slope and I need to form the equation for the model. So the equation for the model would be sales price equals 13439.39 plus 130.12 times living area. Yes. So the question is, for 100 extra square feet of living area, how much do you expect the sales price to increase? Okay, so the slope on the living area is 113.12, so we can expect $11,312.25 increase in your sales price, right? And the fourth question is, what is the forecasted sales price of a 2,000 square foot house? So the living area X equals 2,000. Substituting that directly into the formula, you get $239,684. That would be your sales price. Any question?
Any other questions on A through D? All right. And probably the last thing we'll cover today, but very important, are the regression assumptions. Does this model satisfy the conditions and assumptions of regression? What do you check to check your assumptions and conditions of regression? If it helps, I'll jog your brain. I don't think they call this, I don't think they use this acronym in the lecture slides, but I like it personally. LINE. You're doing regression, putting a line on points. Linear, independent, normal, and equal variance, also known as homoscedasticity. So those are the 4 conditions to check. How do you check them? Oh, sorry.
Is that all right?
Yeah, that's right.
I'm thinking, give a few minutes to try this around with the plots. Then I'll show them the plots, and then I'll probably skip over to R and just do a few steps so that they can see the argument for it. That'll probably be 10 to 15.
I can shoot this up.
I think we're okay.
You're okay.
Because the next slide just has the plots. Thanks.
I like that. All right, if you heard what he said, you can make a plot of the x values versus the residuals. That looks like this. Spot on. All right. Which conditions do we check with the residual plot? Equal variance, as well as linearity. Okay, is this linear? So that red line is the y equals 0 line. It should be flat across that line. Would you say that's linear? I would very much say that's linear. Would you say that has equal variance? It's not perfect, but it's pretty good. Yes, ma'am. Sorry? Oh, yeah, we'll do the code right after this. Or actually, I guess we could just do it right now, huh? All right, so I'll read in my homes data. I'll create my model. Okay, there's my model. I got that original page by doing a summary of this model. Right? Let's get a better looking summary than that. All right, mine's squished a little bit because of my window size, because the font's so big. But that way you in the back can see. There we go. Okay, you've seen that already. So now we want a residual plot, right? Okay, the way we've taught it in this course so far is to take x into the x slot, comma, residuals as your y. RStudio's freaking out because I didn't give it enough room to plot this in the plot window, so we'll try that again. Okay. If you really want that y equals 0 line to compare against, you find that by doing this. AB line, and you tell you want a horizontal line at 0, and I want the color to be red. Okay. So like y'all said, looks pretty linear. Equal variance isn't super great, but it's not clearly violated, right? All right, so we've checked linearity. We've checked equivariance. We check independence and normality. How do we check independence? Kind of a trick question, right? How do you check independence? You can't. Right? That has to be something you know about the data collection. Were these randomly selected homes? If so, they're probably independent. But unless you are told so in the prompt, or unless it's time series data where you can check it, we don't know that. And actually, I did tease that. I did tease in the prompt that these are randomly selected. So, independence, we're good. Normality. What needs to be normal? A histogram. A histogram of what? Residuals. The distribution of your residuals should be normal. You can check that with the histogram. You can also check that with the QQ plot. Is it normal? Mostly-ish. You clearly have some skew on the top end of things, which does make sense given real estate prices, right? You have some homes that are way up in the right tail. So the good news is if you can explain yourself. I believe on your homework you have a question that says check your assumptions, right? And it's not just A, B, C, D, it's explain yourself. So if you point out that this is not the best normal fit, but we're proceeding forward anyway, that would be good. That would get checked. Okay? To do anything with p-values moving forward, that you need to have assumed normality. So you need to have discussed this at some point. Yes? Have you discussed time series in class? Yes? Oh, briefly touched on it? I haven't heard for or against. I mean, if you've covered it in class, then covered it in class. But if it was only for 2 minutes, right? Yeah, if it's highly correlated, then they're not independent. All right. That concludes our covered material for today. I will show you how to do these other plots in R real quick. Note that you can also just use the $ if you're more comfortable with that. Model $ residuals also gives you the residuals. Pick your favorite, remember that one. And lastly, the QQ plot. Excuse me, QQ norm. And then you get the line by doing QQ line. All right. I will post this code. We'll post the slides. We'll even post the video, which you've all been here and watched it anyway. Hopefully you can hear some of the explanations there if you want them. We'll be around to answer questions for a couple minutes. Otherwise, best wishes. There are TA office hours tomorrow from 2 to 4. They will likely be busy. And we'll see you later.